I was told I have a generic monotone voice that doesn't really have much inflection, so I've decided to make an exciting introduction to the videos to keep you all interested. Radio announcer mode, activate. Welcome back to the compositing channel. Generic name, quality ideas. We talk about all the interesting things from color science to image processing. Your home away from home. A safe space for pixels and math, creating quality images from a solid base of understanding. Let the learning commence. So in this video, we're going to talk about stitching spherical HDR panoramas in NukeX with the CaraVR toolset. We'll start with a discussion about what HDR images are and what they're used for. We'll quickly compare the advantages of Nuke versus other stitching software that you might be aware of. And there's a set of raw images we'll be working on stitching, featuring this nice sunny scene. Next, we'll go over a method for how to combine bracketed exposure sets. Then we'll dive right into stitching our spherical panorama using the CaraVR nodes. We'll cover the C camera solver, the C stitcher node, and we'll discuss how to customize what areas of each angle are used in the final stitch. We'll use the C spherical transform node to do some paint work to clean up unwanted items in the scene. We'll do some color calibration, and then finally we'll render out our HDR and use it to light a CG scene in Blender. Let's get started. Cool, so we'll start here with a quick discussion of what an HDR image actually is. An HDR image basically captures the light intensity of a scene from a single point in space. So here's the image that we're going to be creating in this video, and you can see that it has a huge dynamic range from the very brightest sunlight to the very darkest shadow. And this is very useful information when recreating this lighting in a CG environment. So camera sensors capture a very limited dynamic range, usually around 10 or 15 stops between the noise floor and where the sensor clips. Many scenes go way beyond this range. So to capture more range, what we do is we take multiple exposures of the scene and we stitch them together into one image. Also, as you can tell here in this image, we see in every direction. So to create a spherical HDR, we need to capture not only multiple images at different exposures, but we need to capture multiple angles. Often when shooting spherical HDRs, a 8mm fisheye lens is used, which can capture a 360-degree field of view with some overlap in only 3 angles. HDR images are used for creating photorealistic lighting in computer graphics. And they're super useful to do this efficiently. In this video, we're not really going to talk about shooting an HDRI. That's more of an in-depth sort of photography side topic, which deserves its own video. And we're not going to be talking about debayering raw images into scene linear, which is its own separate topic, which deserves an in-depth discussion. To create the images we're working with, I'm using this tool here. So debayer is a command line tool which leverages a few open source projects like OpenImageIO and RawTherapee. So RawTherapee is a really great open source tool for debayering raw images. It supports a lot of features for display referred output like tone mapping and color manipulation, but it can also output scene linear images. It also has quite good debayer quality and a couple of really great options for useful things like chromatic aberration removal. We open up one of these images from our fisheye lens and we go over to the raw demosaicing tab. You can see there's a lot of chromatic aberration here on the edge of the frame, which is very common for fisheye lenses. If we turn on chromatic aberration correction, this autocorrection algorithm does a really good job of removing a lot of the more offensive aberration and is super useful to have in our stitched spherical HDR. There's a lot of options for demosaicing as well. The Amaze plus VNG4 option is a really good demosaicing algorithm that preserves a high level of detail and also avoids artifacts in shadow grain. To get a scene linear output, under the color tab, set the working profile to ACES CG, the output profile to ACES CG, and set the tone curve to a custom gamma of 1.0. This results in a approximately scene linear image. Feel free to play around with it if you like. I'll probably do a more in-depth video on this at a later time. Also, during the video, I'm going to be using the out-of-the-box Nuke config that I built. So if you see a tool or a shortcut that you're not familiar with, it's probably in here. I'll also have this overlay so that you can see what buttons I'm clicking and what keyboard shortcuts I'm pressing, if you would like to follow along with the crazy stuff I'm doing. Great, so we'll move on to why would we use Nuke. When stitching HDRs, there are a few options. There is PTGui, which has been around forever. There's a few downsides to it. It's Windows or Mac only, and often in VFX studios, the main machines that compositors and lighters use is a Linux-based workstation. It has poor quality debayer and not very great color management, and the workflow for using it is a bit convoluted. Sometimes you have to pre-convert all of your raw images to linear 16-bit TIFF and then stitch them together, and it can be a bit tricky sometimes to get good results out of it. It does work though, and it's reliable once you know the ins and outs. But for a lighter or compositor, it's a bit of a pain to try to find a Windows or Mac workstation and use that purely for stitching. I have a couple of example images here which I stitched in PTGui. Compared to the result which we stitched in Nuke, you can see that the colors are very different. And there's also some issues with banding. If you look closely, you can see that the sky is banding and has some noise artifacts. And also in the stitch for the bright values of the scene, you can see noise here and some artifacts in the blending. There's also quite a bit of chromatic aberration, because in the software there's no option to remove chromatic aberration, which is often an issue towards the edges of frame in fisheye lenses. So you'll often see crazy aberration in the stitch like this. Whereas with RawTherapee, you can actually remove that aberration automatically and reliably. And when you're stitching in HDR, the color accuracy is actually really important because the HDR really influences the colors of the lighting in a scene. So it's very important to calibrate the colors accurately and try to get the most accurate result you can. To get an accurate result with PTGui, it's pretty difficult. There's also this cool program, AutoPanoGiga. It is actually really good at stitching and has an algorithm that works really well out of the box. Sometimes it even gets better results than Nuke more quickly, but unfortunately it's no longer sold or developed. There's also limitations for HDR workflows. Sometimes it can be a bit difficult to get proper scene linear imagery out of it, and it as well has poor color management for wide gamut color pipelines. So Nuke provides really good color management and accuracy. It's a familiar tool for lighters and compositors. It provides really good quality, and it has great flexibility because you can pull apart any component, any tool, and really solve difficult problems by breaking the problem down. Cool, so we'll take a look at this bracketed exposure set that we'll be working with. This was shot on a hazy day. There was actually some forest fire smoke that came all the way over to the East Coast. And you can see that the light is a bit more red than you would expect, and the sun is a bit more dim. So we'll be working with these images. You can see that this is a 6-image exposure set, and we have a 3-stop difference between each of the images. You can see that there's 3 angles and a couple of reference images that I shot, which has a Macbeth chart in frame. So this one has the Macbeth chart in the sunlight, and this one has it in the shadow. These are the images we'll be stitching. Cool, so now we're going to move on to discussing how exactly we combine these bracketed set of exposures, all looking at the same scene, into one image which represents all of the dynamic range captured by the camera. So the first step is we need to extract the parts of this image that we want to use. So to do this, we're going to use a luma key, and this generates an alpha channel based on the luminance of the image. If we look at this image closely, there's areas that we don't want, right? If we expose down a bit, we can see that all of the area in the sky is clipped. So the sensor didn't capture any detail here. There is, however, a good deal of really useful information in the shadows because the image is a bit overexposed. So we definitely want to keep those areas. And all of the values in between are pretty good. There might be some issues with motion blur here, but we can remove that a bit later on. So to do this, we're going to look at the alpha channel here, and we're going to bring our parallelogram so that we have the center of the image as a white alpha, we're going to remove the clipped areas in the sky with a bit of fall off, and we're going to keep most of the shadow areas, maybe all of the shadow areas. Maybe not quite all, somewhere around here. So if we pre-molt that, we can see these are the areas of the image we're going to keep. So we'll do the same thing here for the next one down. And this image is a bit darker, but there are still areas in the sun that are clipped. So if we look at our pre-molt, this setup seems to work pretty well to remove those clipped areas in the sun with a bit of fall off. And if we expose up so we can see the shadows, you can see we're removing a bit of information from the shadows here. And we might actually clip a little bit off of the bottom end just to remove some of the more grainy areas, maybe something like this. We'll copy paste this here as well. We'll expose up a bit again. So this is removing a good deal of the very grainy areas from the bottom of the exposure. We might even remove a bit more because it's quite grainy. Maybe a bit more fall off. And then for the highlights, the sun is still clipped, so we're going to remove that. And there's some good information here in the sort of areas around the sun, however, so we'll definitely want to keep that. And we'll go ahead and copy paste this for the other two here. And then for the last one, these are pretty much just capturing detail in the sun. So for the last one, we'll take a look at this. I've actually got the reformats here set to 0.25 scale, so I'll go ahead and set that back to 1 so we can see the detail. So there's our sun in all of the original pixels captured by the camera. And if we look at our keyer, you can see that we're pretty much just removing the noise around it. With this set all the way down, we can see there's quite a bit of noise remaining, which we want to remove. So we'll set it to something like that and see how it goes. And yeah, it looks like we're removing a bit of detail there in the center, so I'll actually bring this up and keep all of the information from the highlights in this image. Kind of like what we're doing here, keeping most of the information in the shadows here. Great, so now we have the sort of areas that we want to keep from each image extracted, but what we need to do is actually change the exposure of each image so that the exposure values match. So remember I said these are 3 stops apart. So what we could do is make an exposure node here and set this to 3 stops, and that should match this image brightness to this image. If we take a look, it's actually pretty good. It's matching pretty well. Obviously there's a bit of motion blur difference, and it looks like the position of the image actually moved a bit. This was quite a windy day, so it's quite possible that with this long exposure time, the camera got blown around a little bit. So what we can do is we can actually use the metadata on these images to drive this exposure change to match all of the exposures. If we look at the metadata, there is the original EXIF data from the camera, and there's also this exposure time metadata key. So this one is a value of 4 seconds, and this one is a value of 0.5, which is a 3-stop difference. Usually when you're shooting HDRs, you'll change the shutter speed only in order to do your bracketed image set. This is because if you change aperture or ISO, the grain profile changes in the images or the depth of field changes, and you don't want to do that because the images need to have the same appearance when you stitch them together, otherwise the stitching will not work. So what we're going to do is we're going to make a multiply node, and we'll change just the RGB because we don't want to change this range that we specified here in the alpha channel. And we'll hit equals here to get an expression, and we'll use a TCL expression. If you do metadata space, then you can specify a key. So we're going to say input exposure time. And this gives us the value of that metadata key. So this is exposing the image up a bit, and if we paste the same thing here, this is actually exposing it down a bit, which is the opposite of what we want, right? We want to brighten this image to match this image. So what we can do is we can take the opposite of that. If we do 1 divided by exposure time, and we paste this here, we can see that this image is being brightened and this image is being darkened. And if we compare the two, they match. That's great, but these images are a bit dark, so we want to actually have control over the brightness of the image. So if we add a user knob, we can add a floating point slider, and maybe we'll call this, I don't know, base exposure. And now we can add this into our expression instead of the 1. So we'll say base exposure divided by exposure time. And this is 0, not what we want. But if we boost this up a bit, we can see that the image is actually getting brighter or darker. So if we paste this onto all of our images here, we can see that they all match. Obviously the grain is increasing quite a bit towards the end here, but fortunately we have already determined what parts of the image we want to use. So even with our crazy grain after the pre-molt, we're only keeping the parts we want to use. And yeah, we're probably keeping a bit too much grain from this image, but we can change that. So what we can do is make a merge node, and if we connect it here to all of our output brackets, we can change this to a plus. And so we're plussing RGB and alpha together. If we look at this and expose down a bit, we can see the result gives us these artifacts where the images blend together, which we don't want. But we have an alpha channel which represents sort of the amount from each image that was added in. And the alpha channel has values above 1, which is normally something you wouldn't want at all. But in this case, that alpha channel is actually tracking important information. It's tracking how much of each image we want to remove. So if we make a shuffle node and we shuffle out the alpha into RGBA and we do a divide, I'll use a divide reverse, which is just swapping the A and B inputs of the merge so that we can disable it. This basically normalizes out the contribution of each image, which gives us back the original appearance. So now if we A/B between one of these images up here and the result, we're seeing something that matches really well. Obviously there's issues with motion blur, which we'll work on solving a bit later, but the result is quite good. And that's the basic outline of how to make this work. Of course, setting all of this up by hand is quite a bit of manual work, so I built a tool to automate that process. If we open this up, you can see there's a few options. One of the cool things you can do with this tool is to select a bunch of read nodes that have exposure brackets and hit sort, and this is going to automatically look at the exposure time metadata on each of the images and try to figure out which images are groups of brackets and then connect an exposure blend up to each bracket. So if we open up one of these, we can take a look at some of the things we can do with this. The brackets is the number of input images, which is set automatically by the sort function. We can adjust the exposure up or down to make it brighter or darker. One thing we'll do before we move on is just make a reformat here and set the type to scale, and we'll turn so that our images are upright, so they're a bit easier to look at. The exposure sets the brightness of the output. The noise floor clips off the bottom end to remove noise from the darker exposures like we saw earlier. And if we expand the keyer ranges here, we can see sort of all of the keyer ranges from the darkest image to the brightest image. And if we look at the noise floor adjustment, we can see it's kind of removing the noise from the bottom. With it at 0, we can see there's a huge amount of noise present from the darker images, and if we boost this up, it disappears. But the fall off, that's sort of the amount of smooth blending. It's the same on each side. You'll note that the darkest image keeps all of the highlight detail. We can set the center to sort of affect where the fall off goes if it's set to 1. By default, it's set to middle gray, but you can bias this up or down if you get better results with that. The defaults generally work pretty well, so it's not too much of a problem if you just leave them alone. So what we need to do is calibrate the exposure of our brackets in order to get a more precise result. It's a bit of a process to properly calibrate a scene linear image. Ideally, what we would do is put a object in the scene, which is an 18% gray diffuse reflector. We would sample the values on that object and set it to a value of 0.18 in scene linear. Fortunately, we shot these two calibration images. We can see that one is in sunlight and one is in sort of the ambient fill from the sky. And our Macbeth chart has an 18% gray reflector as one of its patches. It's the third one from the darkest patch. Normally in a scene like this where there's a colored sunlight, like a sunrise or a sunset scene, you'll get better results by using a Macbeth chart that's shot in the sort of ambient fill from the environment. So we'll use this one that's in shadow. And what we can do is, if we open up our ExposureBlend, we can use one of these other features to create a equalize exposure node. It's the same thing as we did earlier with the expression for exposure and the expression that references the exposure time metadata. Now we can adjust this up or down to see if we can make the value on this patch a value of 0.18. So we'll boost this up a bit, keep going until we get something at about 0.18. It's normal that the values will be a bit different in each channel, so we'll just get it approximately correct here. Now we can copy this value and put it on the other ExposureBlend nodes. So we'll set exposure to this value. Now all of these have the same exposure. It's always good to double check your assumptions though, because you never know what went wrong on set. So if we compare these two, they look pretty similar, but I think that this one is a little bit brighter. So we'll just double check that by finding an object that's the same in each image. Maybe this little patch of concrete here. So if we sample something in this patch of concrete over in this corner, we see it's a value of about 0.55. And in the other image, if we get approximately the same patch, we can see it's actually quite a bit brighter at 0.67 in the red channel. So what we'll do is we'll just manually darken this down a bit until we get to a value of 0.55, somewhere around there. And now we'll use this as our new exposure value. And now if we compare these two, they do look pretty similar. And now we've properly calibrated the exposure of our images. So one thing I'd like to do before we move on is to just fix the alignment issue between these two exposures. If you have to do manual adjustments like this, there's another button here which is useful called Ungroup. So if we click that, it basically takes the contents of the node and moves them out so you have full control over adjusting anything you need to. So we'll just take a look here and compare these two images. If we look at the exposure adjusted ones, we can see that there's a bit of a difference here in the position of the two exposures, which isn't too surprising because it was quite a windy day and I was a bit worried about a car coming through the road while I was shooting this. So not quite accurate, but this should be pretty easy to fix using a simple transform. So I'm just going to put a transform down here because these two images match pretty well, and this one is the outlier that we need to correct. You can see after the stitch we're getting this kind of motion blur looking thing, which we don't want because we want to preserve as much sharpness as we can. So it looks like our rotation is happening kind of around this point. What I'll do is I'll actually do a combination of a transform and a rotate. I'll put my pivot sort of over here, and I'll just transform to align these two as best I can. If you do a wipe between the two images, we can use that to line this up, and then I'll just use the numpad controls. Looks like a pretty good match. And then we'll do another wipe on this side and see if we can rotate this into place. Wow. Yeah, it's better. It's not perfect. To get this perfect, you might have to do actually a corner pin or a more complex grid warp. But for our purposes, I think this is fine. Great, so that's the exposure brackets. If we look here, we have 3 different angles, which we can now start to stitch together into a spherical HDR. So I'll go ahead and copy these nodes up here, and we'll start looking into the CaraVR toolset for stitching HDRs. So CaraVR was a standalone plugin set for Nuke. Its main purpose is to work with spherical images for virtual reality production, and it has a very powerful toolset for doing this. The stitching of this spherical HDR is actually a quite simple application of this type of problem, and in this video, we're only going to be using a couple of the more simple tools of this toolset. As of Nuke 12, CaraVR is included in the NukeX toolset, so we can actually access these tools using NukeX. So to start out, we're going to take a look at the C camera solver node, and this node basically stitches together multiple cameras into a spherical image. I have my resolution of my project setting set to lat long 4K, which is 4096 by 2048. And yeah, a lat long image is basically a spherical unwrapping of a sphere. So it's 360 degrees horizontally and 180 degrees vertically. And this is the format we're going to be creating. So in the C camera solver node, there's a lot of options here. We have a fisheye lens as input, which projects a circle onto the camera sensor. So we're going to be setting up our camera parameters to reflect that. So we say set global parameters. Our lens type is a fisheye. The sensor size is actually pretty important. I'm using a 5D Mark III, a Canon 5D Mark III. You can see here it's in the metadata. And we rotated our image here so that it's upright. So we need to actually swap the sensor orientation. So it's 24 by 36. And the focal length we're going to set to 8mm because the fisheye was an 8mm fisheye lens. There's other film back presets in here as well if you have a different type of Canon camera or a Sony A7S or something like that. The keying section is mainly used for moving footage, so it's not really relevant to us. But just make sure you have one analysis key on the frame that you're working on. Analysis basically determines what the solver can change in order to get a better solution. Orientation changes the orientation of each camera. If we go to the cameras tab, we can see that there's 3 cameras connected, and CaraVR actually stores this in different views. So if you look at the script under the views section, there's actually 3 camera views, one for each camera. And you can switch the views here to take a look at what they are. Going back to main, each of these cameras has a specific orientation. And if we switch to the 3D view, you can see that there's actually 3 cameras set up here. And what the solver does is it changes these parameters to try to figure out a good match for how the cameras were in the original scene. It's kind of like a camera tracker, but just static for our case. So our cameras were actually at 3 different equally spaced angles. And if we change the rotation to 120 for camera 1 and 240 for camera 3, this will equally space the cameras out in 3 different orientations that are equally spaced around the 360 degree circle. So our camera rig looks something like this. So if we say orientation optimized per camera, this allows the solver to change the orientation of each camera input, which is what we want because the camera was changing at each angle. For the focal length, Obviously we're using the same lens for each angle. We're not changing the lens between angles. So optimize single is what you want. It's good to leave this on because sometimes the lens isn't exactly 8mm, and if the solver can change this, it can get a better result. So there's different options here. You can say known focal length, which is going to basically set it to be exactly what you specify. You can optimize the focal length per camera, like if you're using a spherical rig with different cameras or different lenses, this could be useful. But for our purposes, we'll just leave it to optimize single. Lens distortion allows the solver to try to fit the image to match the lens distortion. For fisheye lenses, generally this doesn't help much. I usually leave this off, but for some fisheye lenses and some cases it can help to optimize single. For our purposes, we'll just leave it off for now. And then camera layout. Basically the camera layout specifies how the solver can change the position of the cameras. With a nodal rotation panorama head, generally the position should be such that the lens is at the exact same point in 3D space for each angle, but sometimes it isn't quite perfect, and this allows the solver to change the position subtly to try to get a better result. Spherical layout places the cameras sort of on a sphere around the origin. Free layout allows them to be placed wherever to get the best solve, and nodal layout forces the cameras to be at the exact same position for the nodal point of the lens for each angle. And there's a few other options here for more complex rigs. So generally I get pretty good results with spherical layout or free layout, but if you're feeling confident about the quality of your panorama, feel free to set it to nodal layout. And yeah, actually when we changed the orientation of the cameras, we sort of got an approximation of what our rig is supposed to look like. So first step is to hit match. And this basically looks at each of the input images and tries to find features that are common between the different angles. So we can see that there's these lines that got created. If we click on a couple, you can see that it's actually finding features in each angle and matching them up. So now all we have to do is hit solve, which basically tries to adjust all of these parameters. If we look here, we can see that each camera now has a rotation, a focal length, and a position change. Actually, the position change is null because the camera layout is set to nodal. If we change this to free layout, let's see what happens if we hit solve. It looks like camera 2 and camera 3 are at the same Y rotation, which is clearly incorrect. It's really weird, it's not getting... Yeah, so I actually just restarted Nuke and it seems to be working now. So if we make a C camera solver again, so we'll make a C camera solver, we'll connect it up, we'll set our global parameters, 8mm, optimize per camera, we'll do free layout, we'll do match, and we'll hit solve. Now we have points for each angle. Sometimes it's a bit buggy like that, and you have to just restart or delete the node and make a new one. Anyway, so usually for orientation, I like to put the sun sort of close to the center. And it's pretty important to get the horizon straight, because if it's tilted, everything looks really wonky and confusing. If you go down to this mode, you can actually adjust the horizon to try to get it straight. So I know that this road and this road are at the same height, and this is a bit of a hill. So I'll just line up these two so that they're at the same height, more or less. Yeah, somewhere like that. You can see here the 3D orientation that it figured out for the solve. Now the solve error is basically the number of pixels of air that we're getting. If we look at the points, we can see anything in red is something that's marked as above a certain air threshold, which you can specify here. So if we lower this down, we can adjust what air threshold is marked as rejected. The default is usually a good value. If you hit reject, you can actually delete those points. And then if you hit refine, you can change the solve to try to get a better result based on the latest adjustments you've done. It's also good to just do a sanity check and look at the points. If you take a look here, it looks like this point is significantly different than the surrounding ones. So this, I think, is definitely an error. Yeah, it definitely is. So if you want, you can just kill those by hitting the delete key. This one as well looks a bit different. This one as well, I'm not really sure what it's finding there. These look pretty good. Of course, anything on trees that are motion blurred is probably wrong, so I'm going to kill some of these ones that are on motion blurred trees. All of these go away. This is actually a pretty difficult stitch because of the motion blur. Yeah, that one is a bit off. This one will kill. So after we've made those adjustments, kill this as well. After we've made those adjustments, I'll go ahead and hit refine. And you can see our solve error is down at 2.1, which is actually quite good. We can also add our own points if we want. If you go to the add points tool and hit Control-Alt and click, you can then use this little window up here to add new points. So I'll just go ahead and add a couple so that we see the process. I'll add one right here. You can adjust the size of this window as well if it helps. Sometimes the solve error can actually go up a bit when you refine, just because it's sort of fitting the HDR stitch a bit better, which is not a bad thing. So we'll go ahead and call that good enough. We could do better if we spend a bit more time on it, but for our purposes here, that's probably good enough. You can see that there's these sort of dark artifacts up here. What's causing that? So basically in the cameras tab, but there's this mask section, and if we look, the shape actually says rectangular, which is not quite correct. If we look at one of our views here and look at cam 1 and look at the alpha channel, we can see that the alpha channel that's generated is actually a rectangle, which is a bit odd considering that our input is a circle. So what we can do is select all of our cameras here and change this from rectangular to elliptical. And now we can see, if we do a mask overlay, our alpha is actually a circle. It's a bit big though, so we're going to bring our size down a bit. And we want just enough to capture the whole thing. Our feather is probably a bit large as well. Make this a bit smaller. Bring this down a bit. That looks pretty good. So this mask basically controls what part of the image is used for blending. If we go back to our main view, we can see that the overlay of the boundary of each angle is changed a bit, and we can see that the result has a bit less artifacts and stuff. There are some sort of strange circular artifacts here, but we'll see how that survives once we stitch this together. So to stitch, what we use is a C stitcher node, and this basically outputs a warp and a blend, which tries to combine all of the different angles together into a seamless result. You can see there's still some issues. If we look closely, there's some blending artifacts. If we look here, there's definitely a line that we don't want, and we can see some ghosting on this pillar here. So a little bit of cleanup work to do, but generally speaking, the result is pretty good. Also, you'll notice the resolution is still 4K lat long, and we can change the resolution of each of the steps if we want. So if we change this, let's go up to 8K. It can get pretty heavy if you go higher, especially if you don't have a lot of RAM. But let's go up to 8K and see what the result looks like. So we can try playing around with the masking settings to see if we can get rid of this line. I think we just have a feather that's going out a bit too far, maybe. Let's try bringing down our size a bit. Yeah, you can see that reduces the line a bit. And if we reduce our feather, that actually makes it worse. So maybe our feather needs to be bigger. Yeah, that's reducing it quite a bit. Let's bring this down a little bit as well, just to counteract. That's pretty good. Still a bit of ghosting here. Still a bit of ghosting here. And at some point we'll want to try to get rid of some of the motion blur in the trees as well, which we'll do. But that's looking pretty good. But what if we want to get rid of this ghosting? How do we remove this ghost of a sign? Well, it turns out that before the stitcher, we still have access to each of the views. So if we do a split and join, this splits out all of the views into individual one view nodes. And now we have access to adjust them. So if you look at camera 1 here, this is the first camera, and you can see that there's the sign here sort of right on the edge, which is not great. And if we look at the alpha channel, you can see that the areas that we're using include that sign at a low opacity. Same thing over here. If we look at this angle, we can see that the light pull here is in this angle and in this angle. So we could remove the light completely from this angle if we want to try to remove the ghosting. And for camera 3, this feature that's right on the edge might be a little problematic. So to remove an object from one of the angles, what we can do is make a roto. Just open this up and we'll just cut right along here. It's good to keep the blending on areas of low detail if you can. And we'll just remove this from this cam 1 view. So we'll add a blur, blur it a bit, and then we'll use a channel merge. And we'll set this to stencil alpha only. So we're doing this a bit differently than we might normally do with a normal stencil, because we only want to remove the alpha channel, not the RGB. Just blur this out a bit more. And you'll see why, because the stitcher uses the alpha to determine what parts of the image it blends together. So if we look at the result now with the stitcher, take a look at our sign, you can see that the ghosting here is removed completely. If we turn it back on, you can see this is how it used to be. So it's removing the ghosting on the building and the sign quite effectively. So we'll do the same thing for the light pull here. We'll just cut right along the top here. See what that looks like. So after, before, looking pretty good. So what about the motion blur? Well, to remove the motion blur, we actually have to go back to our bracket blend, and let's go ahead and make a bit more space here. Let's take a look at this. So say we want to remove the motion blur on this tree. Well, to do that, we have to use more information from one of the other exposures that has less motion blur, because all of the motion blur is coming from this last one. So I'll go ahead and expand this guy as well. Let's kill this, kill this, kill these. Connect this up. Okay. So now we have this one and this one. Well, it turns out we can actually just remove areas from these images if we want to get rid of it. So if we make a roto here and we want to just remove a piece of this tree, just get this roto. In fact, why don't we just do this whole part? Everything that's super motion blurred. A bit of blur here, and then we'll just stencil this. So now we've cut a hole in this image completely, but we've also cut a hole in the alpha. And remember, the alpha controls how the blending happens down here. So if we look at the result, we have a very strange looking thing here, but once we normalize, all of that goes away. And you can see with this in there, we're just removing the motion blur from those trees. So that works pretty well. Of course, if you push it too far, you might get weird results. And the reason for that is because in this image, we're actually removing a lot of the information there in the tree. So we can customize that if we want by just overriding the settings here. And let's remove a bit less of the shadow. Maybe bring back a bit of shadow detail here. That's looking okay. And I think we'll do the same for this tree over here. It's working pretty well. And then we'll just see if there's anything over here we need to do the same thing for. Yeah, we'll probably want to get rid of the motion blur on that tree as well. So we'll ungroup this, get rid of this, these guys. Oops. So this technique works really well for more complicated exposure bracket stitches where you have to remove things that are moving, like water highlights is a good example, wind moving in the trees, people moving, stuff blowing in the wind, things like this. And this is really cool because it's super flexible. You can really customize exactly what you want to keep from which image. So getting rid of the motion blurred pieces. Go ahead and remove this as well. What about this one? In fact, to this I think we might just get rid of the tree completely down here because we'll use it from the other angle. So I'll just add an alpha here to get rid of that. Just cutting a hole. And let's look at the result. Starting to use a bit more RAM here. Cool, so the result is looking quite good. I have a lot of the motion blur removed. There's not really much visible ghosting. One piece here which is a little odd. Let's see if we can track that down. Yeah, I think it's the bottom in these two. So we might actually just remove this piece of ground as well. See if that improves the result. Yeah, look, no more ghosting. Yeah, so this is looking really good. If your computer is starting to slow down, one thing you can do is just sort of cache at this point, write out an EXR. When you write your EXR, you have to be careful to not write all of the views. Generally, you only want to write the main view, but all of the views are going to be selected by default. So we'll just go ahead and I have relative paths on here. So this parent directory is set to script directory. So this will work. I'll just put this in render cache. And for the name of this output, I'm just going to grab the first exposure here, grab the name, and call this Smoke Sky. So we'll write this out. One other important consideration when writing out EXRs that are HDR is whether you want to write 16-bit half float or 32-bit full float. And the thing that determines which you want to write is actually how bright your brightest pixel is. So if we expose down a bit here, our brightest pixel in the sun is roughly around 55,000. And this is okay for 16-bit half float. Half float, the maximum value that you can represent is 65,504, I believe. So anything above that number is going to clip to positive infinity. So if you have a pixel that's brighter than that number, you'll have to write out 32-bit full float. But if you want to just use half float for this cache, it's fine. So I'll go ahead and write this out. You have to change the views here as well. It's a bit annoying. Now we can read this back in and keep working. So one thing I want to do is actually remove the shadow by using some paint. So to do that, we will set up a little thing. We're going to make a branch here, and we're going to make a C spherical transform. This is the same as the Nuke spherical transform, except that it's way faster. It's GPU accelerated, and it has a few more features for what types of outputs you want to do. So I'll use that, and we will output something where we can see the shadow a bit more clearly. So what we're going to do is rotate. So our input is a lat long projection, and we're going to rotate -90 in Z and -90 in X. So that puts the nadir, the angle facing directly down, right at the center of the frame. And we can see the shadow sort of placed here, which is cool. But we want to get a bit more detail. So we're going to change the output projection from lat long to rectilinear. And now we can really sort of zoom in and get close up on this shadow for our paint purposes. So we're going to rotate a bit, just trying to get this closer to the center of frame. We're going to be doing clone painting, so we want to have some patch to paint from. I might actually yeah, something like this is pretty good. You can also change the focal length if you go to the output and change the focal here from 16. This will zoom in or out basically. So it's useful if you have a bigger patch. And just remember the settings that you specify here determine the resolution. So if you're concerned about preserving as much resolution as possible, definitely pay attention to that. So this looks good. So what we're going to do is we're going to paint in this space and then invert this transform and merge it back on top of our lat long. So to do the paint, we're going to use a RawTherapee node. And this might be a bit sloppy, but that's fine. So we're going to go ahead and paint and try to remove the shadow. Just going to use the biggest size, set our hardness down to 0, and start painting. Cool, so that's looking pretty good. Now what we need to do is invert this transform. We could just copy and paste this and reverse these values, but there's this cool feature in the C spherical transform which exports a inverted linked transform. So you can just hit create here, and now there's an expression link between these two. And if we connect this up, we can see that when we look at this, it exactly matches the result here, at least within its field of view. We can then merge this back over the top of our result, and we get something that looks terrible. The reason for that is because we don't actually want to take all of the result, we just want to take the area that we changed. So we could do a difference between these two, but there's, by doing a difference node, getting the result here, copying this in as our alpha pre-molting. And that would give us something we could use, which only adjusts the area we changed. But there's this cool feature in the RawTherapee node, which actually outputs an alpha where the paint strokes have been placed. So if we output mask to alpha, this gives us an alpha for where the paint strokes were done. Of course, there's quite a bit of transparency as well. So if we pre-mold this, this gives us a lot of transparency, which doesn't quite fill the whole shadow. As you can see here, there's still a bit of a ghost remaining of it. So what we want to do is make a grade for our alpha with black clamp and white clamp on, and just sort of do a threshold on that alpha value to clamp it up. And this gives us a result which has sort of an expanded boundary. So now we're removing the shadow plus a bit of extra area. Cool, so there's our shadow removed. And by doing this, of course, we are not affecting anything except for the area that we're changing. Well, obviously our width here is maybe a little wide, so we are actually affecting a bit more than we might need to. But yeah, not losing any quality anywhere else. And there it is, our final HDR. So let's write this one out as well. Call this, before we write this out, one thing that we want to do is actually take a look at the color calibration. So the input images are in ACES, and these are being converted to ACES CG on read. So our working space here is ACES CG. One thing we can do is to actually try to calibrate the image based on this Macbeth chart. So to try to do this calibration, what we can do is use a tool called Calibrate Macbeth, which I wrote. It is based on the excellent Color Target tool created by Marco Mayer. And if you take a look here, it's basically a Nuke gizmo. So it basically does a linear regression analysis on the color points. It tries to do a best fit to fit the patch in the image to the patch value that the calibration should be under D65 lighting. I'm not going to go into detail here, but suffice to say that we could try to do a calibration with this shadow version, assuming that the light from the sky is somewhere close to D65, which I think that it is. So we're going to plug this in, and basically what we do is we find the corners. If we look at the output here, it shows you the color. So it looks like our orientation is wrong. This one is up here, somewhere like that. It's a bit fiddly. And there's not a lot of pixels to work with here, so we're just going to try to match it as best we can. Trying to get it exactly in the center so that we aren't biasing our results by the defocus in the image, which is blending the colors together. This looks pretty good. So what we're going to do is basically just make sure that our color space is set to ACES CG, and we're going to calibrate the chromaticities only so we don't change the exposure of the image, because we already did that with our calibration here, and we're just going to hit calculate. And this gives us a bit of color change. It's actually changing the intensity of the greens and yellows quite significantly and removing some of this purplish cast from the sky. There was a neutral density filter on the lens when this was shot, so it is quite possible that the colors were being changed by that filter. This change does actually look pretty good and more similar to my memory of what the colors looked like. So we're just going to create a color matrix from this. We'll ignore the multiply part since we already calibrated the exposure, and we'll just chuck this on down here. Looking pretty good. Now we can write this out, and we'll go ahead and write out in the ACES color space, which is ACES 2065-1. And this will convert from ACES CG to ACES on export. Great, so we'll just render this out, making sure we're just rendering our main view. And it looks pretty good. Next, we'll take a look at how this HDR might be used in a simple lighting environment. All right, so to test out our HDR and see how it works, we're going to be using Blender because it's easy and free, and I'm not a CG person as much as a compositor, so I like to keep it easy. So we are going to use a pre-made scene. If you go to blender.org, download demo files, there's this junk shop, which was a splash screen for 2.81. And you can actually download the actual scene with all the lighting and textures and everything. So we're going to try opening this up and swapping out the lighting with our HDR and see how it looks. So I have the scene downloaded here, and I'm just going to open it up. So here's the scene through the camera. If we switch up here to the rendered view, we can see the scene. So what we're going to do first is just turn off all of the lights. It should disable all of the lights in the scene that are currently being used, except for the self-illuminating shaders. I'm just going to make a new shading workspace. I'm just going to switch quickly to world here, and we're going to get rid of this black body shader on the background in the world. We're going to press Ctrl T with Node Wrangler. We get our environment texture and coordinate mapping. We're going to go to open, going to go to our HDR that we rendered out. We'll set the color space to ACES. I have an OCIO config loaded in Blender. You can do that under the color management over here to customize the view transform that you're using and everything. We'll set the strength of the background to 1. And we're going to go into the render tab. We'll turn on adaptive sampling, set this to a low value. We're going to set the denoising to open image denoise, and we'll turn it on for viewport as well with a start sample of 32. And let's go into the camera. We're pressing 0 on the numpad. Just zoom in a bit. Now if we switch to the rendered view, turn off the overlays as well. So this is lit purely by our HDR, and it looks actually pretty good. To prove that to you, if I disconnect the HDR, it's black. So I'll just connect it back up, and let's try rotating our HDR around a bit. In Blender, Z is the up axis. So we'll rotate this. We should be able to just drag it and get somewhat of a real-time interaction. Can make the sun come from a slightly different direction. Maybe get some nice edge lighting on here. That's looking pretty cool. So all of that purely with our HDR as lighting. Can even rotate around our camera, get a different view. I really like the reflections on this metal robot over here. Looks really good with the blurry reflections of our HDR in the background. There's a lot of really great detail in this scene. Could be more of a midday direct sunlight look. More of an early morning look, lit from the side. Love the shadows and detail we're getting here. So yeah, this is the end of the video. Thanks for watching. I did go into a lot more detail here than might be necessary just so I can show you how to solve the problems you might come across. So don't expect that every stitch is going to take you an hour of manual labor. Oftentimes you can get a stitch quite fast if the source images are well shot. But yeah, we can see that the result we have here is a very high quality stitch with proper color management and very few blending artifacts and very few chromatic aberration issues. So I think the results speak for themselves. And that's the end. Thanks for watching. Bonus round! So I just wanted to share another scenario with you. Sometimes there are sets of images which when you try to get a good solve with the C camera solver, it just won't work. The more manual matches you add, the worse it gets, and it just doesn't cooperate. So with the C camera solver, there's always a manual workaround. I've already blended these exposure brackets together, so we don't have to do that. So we'll make a new C camera solver. Set this up real quick. Hit match, hit solve. And you can see out of the box we get an okay result. If we try to line these up so that the horizon is flat, this is a good case for the horizon because we have an ocean in view, so it has to be at exactly the horizon level in order to be correctly aligned. That's looking pretty flat for the center, but if you look on the edges, you can see that it's not lining up correctly. This side goes up, this side goes up. So if we hit refine, hit reject, hit refine, this is going to give us a little better result, but still these aren't lining up. We could even try to add some features. Expose down here so we can see what's going on. One on this rock. Hit refine. Now everything in the sky goes out. Maybe we add one here. Refine. It's a little better. Refine. Not much changed. Let's see about over here. Refine. Refine. It's not so bad. We could try to line that up. The center is working pretty well, but now this slopes down. Try to add another feature. When you add user matches, usually they're weighted higher in the solve if you have this user matches weight set high. So one user match will generally influence the result pretty significantly. It's a little better. Try to line this up again. It's actually not so bad, but this is still a bit out. Try to add another user match over here to force it. A little better. Try to line it up again. So that's not terrible. Let's try to put a C stitcher down. See how that looks. It's okay, but we're still getting some ghosting. And if you look carefully, this is pretty straight, but the horizon sort of goes up over here. So long story short, you can get an okay result, but there's another approach to this, which might be quicker in some cases and doesn't involve a whole bunch of manual user matches. So what we can do instead is, if we just kill this completely, or maybe just copy it off to the side, we'll make a new camera solver, connect it up, set our settings, free layout, 24, 36, 8, match, solve. Set this to elliptical. That gives us a result. I could just move this over to the center. And what you can do is actually manually align each camera. So if we turn off our two other cameras and just use camera 1 to start, I'm just turning off the enable switch here. Let's try to line up this one. To get the horizon as straight as possible. Looks pretty good. Now if we switch to the camera mode here, that gives us a little circle for the camera. And if we turn on camera 2, now we have the result of our alignment from the auto solve. And what we can do is select camera 2, and you can see it selects it down here. And now we can actually just move it. If we hold Control Alt, we can actually move only this camera and try to line up the two images. So if we move over here, just trying to line up this feature. It's pretty good, and then I'll just drag this side down so we rotate it a bit. It's a bit too far. You can see the ghosting here. Sometimes you can toggle it on and off to get a better idea of how your lineup is. Looks okay. And we'll do the same for camera 3. So I'll select camera 3, move the whole thing down. And you can see it's just changing the rotation values here. Just looking at this to line it up. Sometimes you can go full screen to get a better view. Let's toggle it off. Line this up. Looks pretty good. And once you have a pretty good result, just double check our horizon again. Looks quite good. Now we can just do a C-stitcher. And you can see the result is quite good. And we've fixed these weird sort of horizon alignment issues on the edge images. So this sort of more manual approach is a really good option for the more tricky stitches that just won't cooperate and won't do what you want them to do with manual matches. And it's a good strategy to have in your toolbox for the tricky ones.